So it is my pleasure to introduce our second speaker, Dusa McDuff. She got her PhD at Cambridge, and she is currently a Kimmel Professor of Mathematics at Barnard College, Columbia University. And she is an eminence in the field of symplectic geometry and symplectic topology. So her scientific accomplishments have been recognized by our mathematical community through many different awards and honors. Just to name some of them, she was elected Fellow of the Royal Society in 1994, and in 1998, she was a plenary speaker at the International Congress of Mathematicians in Berlin. Since 1999, she has been a member of the National Academy of Sciences, and in 1991, she won the Sutter Prize awarded by the American Mathematical Society. Some other prizes. In 2017, she won the Steele Prize for Mathematical Exposition, also by the EMS. In 2018, she received the Sylvester Medal of the Royal Society, and we could go on. The list is quite long. And also, beyond all these academic achievements, she has been very active in encouraging and supporting the participation of women in mathematics in many different ways. So we are very honored with her presence here today. And the title of her talk is Embedding Problems in Symplectic Topology. So whenever you want.
Well, thank you very much for that introduction. I'm going to talk about something completely different. So I hope you enjoy it. Okay, so let's get share my screen and let's try my talk. Oh, okay, so then I want to go into full screen mode. Full screen mode. View, enter full screen. Here we are. Okay, so this is something completely different. I wanted to tell you a little bit about symplectic geometry, which is an area in which I've been working for a long time. It's a field that started developing, I mean, it has its roots in the 19th century, as you'll see, but it became interesting with work of Gromov. I'm going to explain a little bit of the history. And now it has developed enough so that there are a few applications, actually. I mean, in certain kinds of problems, you might want to take into account symplectic geometry, the symplectic, not just Euclidean geometry. Anyway, so let me explain. So what a symplectic structure, it's a rather elusive geometric structure that you can put on an even dimensional space. And I'm going to describe some basic properties of the structure, fundamental results, and then discuss some open problems, one of the ones I'm working on at the moment. So first of all, an introduction. So let me contrast it with Euclidean geometry. You all know Euclidean geometry, very familiar. It's what introduced me to mathematics. It's so beautiful. So it's got lengths and angles and distance measurements and circles and beautiful theorems, right? And it's based on the inner product of the inner product of two vectors, which is the length of the product of the lengths times the cosine of the angle between them. And then we have Pythagoras' theorem telling you that the length is given by the sum of the squares, the square root of the sum of the squares. And the dot product, the important thing, it's symmetric. So the dot product of V and W is the same as the dot product of W and V. And that's the basis of Euclidean geometry. But in symplectic geometry, you use a different product. You don't use the dot product, which is symmetric. You use an antisymmetric product of two vectors, which, the omega zero of two vectors, VW, is if you interchange them, it changes sign. So you don't have a notion of length. But what this thing is measuring is a signed area. So that's the measurement you have. And the basic example is on Euclidean space, you have standard area, which you can take as the determinant of the vectors. And it's just an area. And its sign depends on orientation. So if you change the two vectors, its sign changes. Now, okay, that's in 2 dimensions. You have an area form. But in 4 dimensions, you also have a 2-dimensional measurement. And you do something very simple. You just take some 2-dimensional surface in R4 and you project it onto 2 directions, say x1, y1, take its area. And then you add what you get when you project it onto the other 2 directions, x2, y2. So it's a very odd kind of measurement. But you get a form. This is written as dx1 wedge dy1 dx2 wedge dy2. That's a closed form if you know some differential geometry. So that means that by Stokes's theorem, if you have a disk, it just depends on it's a length. The integral of the form over the bound over the surface is just given by the integral around the edge, because it's actually an exact form in Euclidean space. So it means that the measurement you get a measurement of area, but it's very flabby. You can move your thing around. If you keep the boundary fixed, it remains the same. So you get these very flabby measurements. And if we look at it as a four-dimensional thing, you're trying to make measurements in 4 dimensions, different directions are different. So if you take the x1, x2 plane, it's Lagrangian. I draw a picture here because if you take this plane in x1, x2 and you project it down to x1, y1, it's just a line. It doesn't have any area. And if you project it onto the x2, y2 plane, it also doesn't have any area. So that's what's called Lagrangian. It doesn't, the symplectic form vanishes on it. So we have a geometry in which the directions are not all the same. That it's not a sort of isotropic geometry, which we're used to in Euclidean geometry. And in higher dimensions, in R6, for example, you do exactly the same thing. You group the things in pairs, and you take the measurement in the first 2 plus an area in the second 2 plus the area in the third 2. And why on earth would you do such a funny thing? Well, it comes from physics. The point is that the pair x1, xy represents the position and velocity of a particle in one direction. So if you have a particle moving in 3 space, it gives 6 coordinates. And what you're actually measuring is some kind of entanglement of the 2 things, position and velocity. So that it really, I mean, the whole geometry came from physics, which I'll explain in a little minute. But that's what you're measuring. So it's if you're thinking of ordinary geometry, it's a bit mysterious. So if you just in general, if you have it in even dimension, 2n dimensionals in Rn or some more generally some manifold, you get it's a closed non-degenerate 2 form, and so it means that d of it vanishes, and it's non-degenerate means that it sort of encompasses all the possible directions, so you get a volume out of it. And if you have a function on your manifold, then it generates a flow. You get a vector field, and you get then a one-dimensional family of motions that goes along in the direction of that vector field. And that group of motions preserves the symplectic form. That's the essential geometric thing. So you get, these are called symplectomorphisms. They're diffeomorphisms that preserve the symplectic structure. And this flow is a solution of Hamilton's differential equations, which are very well known in classical mechanics, and generated by this vector field, which is given by, you take a function h, dh is a one form, and then you use omega to give you a vector field. And so in Euclidean space, you get the standard Hamilton's equations. Dx by dt is dh by dy, and dy by dt is minus dh by dx. You might be used to these with p's and q's coordinates, position and momenta coordinates. And for example, in Euclidean space, if you take the radial function, then so it's the radius, then the flow is a clockwise rotation, and it preserves it always, this flow always preserves this function h constant. So that's the basic examples, but there are many, many more symplectomorphisms. That's the easiest kind because your vector field can depend on time and things. And so that means that if you have a symplectic space, there are lots of ways you can move it in order to preserve that symplectic structure. So it's very, very different from Euclidean space in that way. So where does this come from? Well, it comes from 19th century classical mechanics, that this was a way of formulating the equations of motion, because the flow phi h of t describes the time evolution, t is time now, of a mechanical system where the energy function is given by h. So h is a function of position and velocity, and energy is conserved as the system evolves with time. And this picture is due to Hamilton. typically. I mean, he was the one who formulated it this way. And it was used, for example, by Sonia Kovalevskaya when she was solving classical, trying to understand how a top moved, spinning tops, very complicated equations with 6 variables, but you can use a symplectic structure to simplify the equations and solve them, which is where I first came into contact. I didn't realize I was doing symplectic geometry, because if you're doing classical mechanics, you don't use that language, but that's what you're doing. So let's skip forward quite a bit to the late 20th century, when very deep and subtle connections between symplectic and complex geometry were first noticed and exploited by Gromov, who's this brilliant geometer many of you probably know. So complex geometry is another geometry that's sort of two-dimensional, because the complex numbers are two-dimensional. And this relation gave rise to a main tool in the modern theory, which we call J holomorphic curves. And so here's a picture of Gromov on the left and Fleur on the right. So Fleur extended these ideas to develop an influential version of Morse theory for spaces of loops and paths in a symplectic manifold. And that's called Fleur homology. That comes up in many, many discussions of symplectic geometry. If you want to make measurements, if you want to understand things quantitatively, that's a very good tool to use. And these new concepts are the basis for the relevance of symplectic geometry to string theory and mirror symmetry. So, symplectic geometry started off from classical mechanics, but it is still incredibly relevant to today's theoretical physics because of the kind of structures that people have discovered. Why is symplectic related to complex geometry? So let me just explain a little bit. You think of R2 as the complex numbers. So you've got variables x and y, and you take x plus iy, that's the complex numbers. And then there's a relation between the symplectic form and the dot product of I and V. So the symplectic form is an area. So it's the length of V times the length of W times the sine of the angle between them. The dot product is the same times the cosine of the angle between them. But if you take the dot product if you rotate V by I by 90 degrees, that's multiplying it by I in the complex numbers, you get the dot product. So you have a relation that the symplectic measurement is this area of this gray rectangle, and the IV is there, and the dot product is the angle between them. And so Gromov discovered, complex structures are very rigid. Not all manifolds have complex structures, and you can't expect what you're doing to preserve a complex structure. But you can perturb the complex structure to what's called just to the tangent space level. So you think of, here I'm multiplying tangent vectors by I, so that's rotating them by 90 degrees. Well, you could rotate them by some other way, use some other transformation. All you need is that if you do that transformation twice, you get minus the identity, because that's the whole property of I squared is -1. So you look at this more general kind of complex structure, an almost complex structure, and to me, interesting in symplectic geometry, it's meant to be positively related to the symplectic form, so that if you take the symplectic measurement of a pair VJV, it's positive. So that's like that if you take the length of it, and an analogous thing is if you take omega 0 of VIV, you just get the length of V squared. And so there's almost complex structures. And so now we have extra structure. We actually get a metric. We have an idea of a geodesic. So a geodesic is now one complex dimension. So it's not real anymore, because we're working sort of in two-dimensional geometry. So they're J holomorphic curves. So they're curves where the tangent spaces of the curve of the two-dimensional object are invariant under J. So if J were really a complex structure, then that would mean that C was actually a complex complex curve in the usual sense in algebraic geometry. But here we've weakened J, so it's not integrable. But you still get interesting curves. So in the complex plane, any polynomial and complex variables gives you a curve. But the point is that J is very flexible, so that you can take any symplectic manifold, find a J, and then start looking for these J holomorphic curves, which allow you to give a way of probing the geometry of the space and understanding its structure. They're the basic tools of the modern theory, how to understand these complex curves. And they're actually solutions of because they're solutions of a Cauchy-Riemann type equation. So they occur in finite dimensional families, and they behave relatively well under when you perturb J, because J is not fixed. J, you fix omega and you choose a J, any old J. You look at the curves you get, you perturb J, and then you're looking for things which don't disappear when you perturb. You want robust things that will give you a way of allowing to make measurements, because the point is that if you have a J holomorphic curve, the symplectic form is always positive on a J holomorphic curve, so it has a well-defined area. Anyway, so what are special features, just to wrap up the notion, sort of general discussion of symplectic geometry? It has two faces. It's got the symplectic face where it's related to complex geometry, where you look at submanifolds where the restriction of omega is non-degenerate. And then there are these Lagrangian submanifolds, which are half-dimensional, and the restriction of omega vanishes. So they're like totally real objects, and they have a lot of relation to dynamics. Then there's a tight connection with physics. I mentioned Hamiltonian dynamics in 19th century, which is where it came. And then there's a lot of duality, mirror symmetry in string theory today, which is reflected in the structures in symplectic geometry, even if you're doing nothing to do with physics. Then there's Darboux theorem, another 19th century theorem, saying that all symplectic forms are locally the same. So there's no local structure. And then we have the group of symplectomorphisms, the transformations that preserve the structure. That's infinite dimensional. And the interesting thing is that, you're using the differentiable structure to define omega, because omega is a two form, right? It uses differentiable structure. But if you look at a symplectomorphism, so that's something that preserves the symplectic structure, it's actually, that group is closed in the uniform topology. So it means that actually to describe when something preserves a symplectic structure, you don't need derivatives. You can make a measurement in the space, which if your diffeomorphism preserves it, it'll make it symplectic. So that means that symplectic structures are very robust in a sort of interesting way. So there's a notion of symplectic capacity, which is a measurement of the size of a set, so that if omega preserves a capacity, if a diffeomorphism preserves a capacity, it preserves omega. And this condition just doesn't involve derivatives. And so it means that symplectic geometry in many ways is a topological theory. And you have a very interesting interplay between rigid things, where things you can't move them, and flexible things where anything goes. And I'll show you a little bit about that later. But that's partly, there are very interesting structures in this geometry. So that's my brief introduction to symplectic geometry. And let me just tell you some absolutely basic results related. I mean, it's a huge field now. It's developed in many, many different directions, and I'm only telling you a little bit about it. So let's look in 2 dimensions. So you have an area form. And so that means that if any surface which is oriented has a symplectic structure, an area form, which is unique up to a scaling factor. So there's nothing really interesting. And there are lots of area preserving diffeomorphisms. And here's a typical theorem by Moser saying that if you have a closed disk, which is diffeomorphic to a closed region of the same total area, so we're in 2 dimensions here, then there's an area preserving diffeomorphism from D onto U. In other words, there are no invariants, apart from topological ones. If you have a region in space which looks diffeomorphic to a disk, then it's you can find an area preserving diffeomorphism to a disk of the right size. So the situation, the point is, in higher dimensions, the situation is really different. So we have this famous theorem of Gromov, which is called the non-squeezing theorem. So we take a ball in Cn, R4 or R6 or R8 or something, and we measure it by A. Here is an area measurement. So it's the area of a slice, a standard slice through the center. And we want to try and embed it into a cylinder, which is a product of a two-dimensional disk of area big A times R2n minus 2. And the question is, when can you do that? And you can, obviously, if little a is smaller than big A, you could just embed it, just embeds in. And the question was, could you ever take the big ball and squeeze it into the cylinder? And of course, it's called the non-squeezing theorem. The theorem is that you can't. So this is something that Gromov found tools to prove this, to say that you can embed the ball in the cylinder only if the size of the ball, the area of the slice of the ball, is less than the area of the slice of the cylinder. And of course, if you do in volume preserving, you can, because what you can do in volume preserving, you can shrink in the first coordinate and expand in the second coordinate. And then, and that's a volume preserving map, and that will squeeze in the first area. So it's a clear distinction between symplectic and volume preserving geometry, which is one of the things that Gromov was trying to get to. Another thing is that you can think of this as a form of uncertainty principle, because the size of the cylinder, that A is the area of the what's happening in the first two directions, which are velocity and momentum in the first two directions. And what you're saying is that if you have something which is where velocity and momentum in B2NA, which are all bounded, but you can't sort of get more information in the first two directions by giving up information in the other two directions. So there's a physical interpretation to what this says. So actually, you might think of it as a curiosity, but it's actually a very basic result. So there's a notion of a symplectic capacity, which is you take, given an open subset here of Euclidean space, take the maximum of the size of a ball that embeds in. That's a measurement. That's a symplectic invariant. It's two-dimensional, so essentially two-dimensional in the sense you can take this cylinder of infinite volume, which has got finite capacity, and any diffeomorphism that preserves a symplectic form up to sign. That's what you can prove. So this is the measurement you can make that will pick out things that preserve the symplectic structure. And so that opens the door to a whole very interesting new area about trying to understand homeomorphisms that preserve a capacity. So just topological maps that preserve a capacity. And there's been a lot of interesting developments in that area, which I don't have time to go into. Okay, so I want to talk about what I've been working a lot in these embedding problems, because once we have a result like this, we've got some kind of measurement. You want to know, what does it mean? Suppose I try and embed, well, I understand what happens if I try and embed a ball into a cylinder. What happens if I try and embed lots of balls into K balls into another ball the same size? When can you do that? What are the obstructions to doing that? And that problem was solved in the 1990s. But then there were other things. So the next sort of simple shape is an ellipsoid. And so I spent a huge amount of time trying to understand about how to embed ellipsoids, especially four-dimensional ones, which are very interesting. But now we sort of understand four-dimensional ellipsoids, you can look at higher dimensions, which is very unknown. So an ellipsoid, it's like a ball. It's just that you have two, it's a distorted ball. So it's got one measurement A, which is the smaller area slice, and you've got another measurement B, which is a bigger slice. And any ellipsoid, which, if you take any positive definite quadratic form and you look at the surface it gives you, you can always just linearize it and make it look like this. So this is a model for any ellipsoid in 4-dimensional ellipsoid. And the question was, when does one ellipsoid embed into another? So that, it's just a slight generalization of embedding balls into cylinders or something. And so Hofer thought about this, and he had some wrong conjectures, but finally he had a right conjecture, and he conjectured that the answer is that one ellipsoid with size A and B embeds to another one with size C and D, if and only if some numerical condition is satisfied. And this numerical condition is, for AB, you get a sequence of numbers, NAB. For CD, you get another sequence of numbers, NCD. And the claim is that the numbers NAB should be pointwise less than the set of numbers NCD. So what are these numbers? Well, NAB is a set of all numbers of positive, non-negative linear combinations of A and B. So it's all KA plus LB, where K and L are positive, and you arrange them with multiplicities in increasing order. And so these are actually measurements of you have a Hamiltonian flow around here, and it's measurements of the lengths of the orbits of that flow. So if you take N22, then the numbers you get are 0, and then you get 2 different copies of 2, because you can take K to be 1 and L to be 0, or L to be 1 and K to be 0. Then you get 3 lots of 4, because you've got 2A, you've got A plus B and 2B, and then you get 4 lots of 6 and 5 lots of 8 and so on. And if you compare that with N14, then N14, you have, all the multiples of 1, 1, 2, 3, 4, but you get another 4 because you've got this second B is 4 now. And then now you get 2 ways of writing 5, because you can write it as 5 1s and 1 plus 4. So you get 2 5s, 2 6s, 2 7s, and then 3 8s. So you can write down the sequence. And you can see that N22 is pointwise less than or equal to N14, and so that tells you there's an embedding, if you believe the conjecture. And so these numbers are not just completely drawn out of a hat. There's a homology theory called embedded contact homology, which is a kind of Fleur. I told you Fleur developed this theory of sort of there's homology theories using his J-holomorphic cylinders, and it's a 4-dimensional Fleur theory, which is related to gauge theory, which is another invariant in 4 dimensions. And the generators of this are unions of the closed orbits of the boundary Hamiltonian flow. So we have a well-defined kind of generalized homology theory, and these are the actions of this ECH generators. And so the conjecture is that you can make this embedding. In other words, when you can make this embedding is entirely seen by properties of the boundary, that you have this invariance. And I proved this conjecture some time ago. So first of all, I had to figure out how you could embed ellipsoids into ellipses, how you analyze that problem. And then it was some numerics to prove the conjecture, using results actually of Hutchins about embedded contact homology. But to explain what it means, it gives you very interesting answers. So if you look at what's called the embedding capacity function of a ball, so you look at a fixed ball of size mu, and you try and embed you try and embed an ellipsoid E1A. So A is a measurement of the eccentricity of the ellipsoid. So fix A. You've got some ellipsoid of it's larger axis has got side 5.4.3 or something, 5.43. And then you try and take the smallest ball you can embed it into. And that gives you, if you take the infimum of these sizes, that gives you a number. And so that's called the embedding capacity function. How big do you have to make the target in order to embed a particular given domain? And the function, it was obviously an increasing function, but I worked it out with Felix Schlenk, and we were really surprised by the answer. Because instead of just getting a general increasing function, this proper function has a lot of structure. It starts off with this sort of stepwise thing, but first off a line through the origin going from 1 to 2, then it's flat until 4, and then it's a line going through the origin from 4 to 5, and then it's flat, and then it's a line through the origin from 5 to, this is actually 6 1/4 to some other next number, and you get an infinite sequence of steps there. And then the convergent point is this tau to the 4th, where tau is the golden ratio. And then you have a sort of indeterminate region here, which I won't describe. And then after 17/6², there are no obstructions except for volume. So that whatever there was in this ball that meant that you had to enlarge it to embed the ellipse sort of disappears eventually. So that structure there is an illustration of rigidity to flexibility. So in other words, if your ellipsoid is rather fat, it's small and fat, then there are obstructions, but if it's long and thin, you can do whatever you want. And to be more specific, you get this whole sequence of steps here is the numerics of it are based on the Fibonacci numbers. So they're completely described. I don't want to tell you what they are, but they're completely described. After 17/6², there's no obstruction. And then in the middle, you get some transitional region between rigid and flexible. And so that's what you get in 4 dimensions. The analogous problem in 6 dimensions, where you'd now perhaps take an ellipsoid where you'd fix one and then you'd have 2 parameters, A, B, that you could vary, and you'd want to know how big a ball does that embed into. That's just completely unknown. We don't have techniques to deal with that. I mean, I'm going to tell you at the end about some result I have, a sort of an approximation of this problem, but the general result is what the answer should be is unclear, because there's an analog of Hofer's conjecture where you just take the 3, instead of taking combinations of the 2 sizes, you take combinations of the 3 sizes, and you look at that numerical sequence. And that is simply wrong, because Guth found some very clever embeddings, which embeds E1 and S can be as large as you like into something slightly bigger than E3 and E3, and then S, you just put in S cubed to make a large thing. So the point is, if you take an ellipsoid which is small in one direction but large in the other 2 directions, you can embed it. Hind is very good at making embeddings. He found explicit embeddings into this, which is a 3-ball times some large Euclidean space. Okay, so now we look at the stabilized embedding problem, where we say it's far too hard to decide what happens when you take an arbitrary 6-dimensional ellipse. So let's take a 4-dimensional ellipse, but multiply it by a Euclidean space, and then try and embed that into a 4-dimensional ball times Euclidean space. And so that's a simple version of the problem, where your ellipsoid E1A, and then your 3rd coordinate you don't care about. It's as large as you want. And the target now is not a 6-dimensional ball, but it's a 4-ball times something large as you want. And then, so we can look at this function, and this is the function that we've been trying to understand, because it's more amenable. We've at least got some tools. The idea is you can do things in 4 dimensions, and then if you're lucky, they'll persist in higher dimensions. So Christopher Gardner and Hind were the first to notice that the Fibonacci stairs stabilize. So in other words, that the obstructions you get to embedding in 4 dimensions are sufficiently robust that they will continue to be obstructions, and those are the only obstructions in higher dimensions. And then Hind, he's very good at making embeddings, and so he showed that whatever this function is, when A is sufficiently large, so bigger than tau to the 4th, then there's a folding curve, which is 3A over 1 plus A, and you can put the curve inside that. You can get it in there. So an explicit construction that allows you to make that embedding. And if you compare this, you see that if you look at this function 3A over 1 plus A, that's this graph of F here. It's this curve going up here. And it crosses, there's always in 4 dimensions a volume obstruction, which is this dotted line. That's a square root function. And it crosses the square root function exactly at tau to the 4th. Now, if you stabilize and the volume obstruction goes away, so you're seeing sort of what can you see when there's no volume obstruction. And all the obstructions, the Fibonacci stairs, it's a bad drawing, but these peaks actually lie on this curve F. So what happens is, in 4 dimensions, the graph sort of ping pongs between these two things, between these two curves, and then eventually in 4 dimensions it settles down to the volume curve, but in higher dimensions you don't see volume, and the conjecture is that it should settle down to this folding curve. So that's what's called the stabilized embedding conjecture for the ball, that you should you should be able to calculate this function, and that when a is bigger than 2 to the 4th, it should simply be 3a over a plus 1 plus a. And I prove that this is true for all the integers, like 8, 11, 14, and so on. And then I proved with Christopher Gardner and Hind that it's actually true for this sequence. These are the odd Fibonacci numbers. Our Fibonacci stairs were all based on the even Fibonacci numbers. These are the convergence to 2 to the 4th from above. So this is a very nicely related sequence, related to the Fibonacci numbers. So that was proved with a lot of difficulty, I have to say, in 2017. Now, recently, so how can we do this problem? I was going to tell you a little bit about this problem, sort of what kind of methods we're using to tackle this problem. Because in a way, the methods are, it's a nice geometric problem, but the methods are sort of interesting. So we know, for one thing, that if you stabilize, the embedding function has to go down, because you can just take an embedding of E1A into a ball and then multiply by the identity. So we just have to, if we want to prove the Fibonacci stairs stabilize, we just have to show that whatever reason there was, that, there's a reason why you need the ball that size at these peaks. At these peaks here, there's a reason, there's an obstruction that tells you that you've got to have, the ball's got to be this size and got to be that size. That obstruction would have to stabilize. Okay, so we need to find what we call stable obstructing J-holomorphic curves. The reason why the obstruction stabilizes is that we can find some curve in the complement of the ellipsoid, which, because it's J-holomorphic, has got to have positive area. So that means you've got to make if you put an ellipsoid in, you've got to make the ball big enough to accommodate this curve. Right, typically, actually, we compactify the ball into CP2. So we're working in complex projective space. But the idea is you find curves in there which live outside the ellipsoid, and they've got to have positive area. So that means that if you've got a big ellipsoid, your ball has got to be big enough to accommodate that curve. And we've got much better understanding of curves in 4 dimensions than we do in higher dimensions. So partly because in 4 dimensions, we're looking at 2-dimensional objects, which when they intersect, have to intersect positively, because they're both complex, and so you can't have a negative intersection of 2 complex objects in 4 dimensions. So that's, you just know much more. So if you have a curve, we're usually working in CP2, the compactification, it may persist when you perturb things in 4 dimensions, but it often disappears when you multiply the target by R4. But Hein Kerman and Christopher Gardner find a useful criterion that guarantees the persistence for certain curves. So that means we have a nice condition for what kind of curves we need to look for that would persist. And so all we have to do is find these curves. So how do you see the obstruction? Well, we take an ellipsoid E1x and we embed it in CP2. So we just take a ball and we compactify its boundary to make it into a complex line, and we embed the ellipsoid in it, and we can make mu very big, so we have a big ball. And we remove the interior of the ellipsoid, and then we we sort of, if you like, we want to say is you have an ellipsoid, you can stretch the neck. You just deform the symplectic structure so that the neck, the boundary, the collar boundary of the neighborhood becomes infinitely long. So you can either just say you're stretching the neck, or you can say you're attaching, you take the complement of the ellipsoid and attach this negative end, which is the boundary times from -infinity to 0. And that negative end is getting shrinking. It gets smaller and smaller as it goes down to this ellipsoid. So that's a sort of non-compact manifold, but there's a Hofer analyzed curves in these non-compact manifolds, and if you impose some finite energy condition, you have a very nice theory, and showed that they have to, the negative ends of these things have to be asymptotic to the periodic orbits on the boundary of the ellipsoid. So there's a Hamiltonian flow on the boundary of the ellipsoid, there's some periodic orbits, and it's got to converge to that. And if you choose an ellipsoid where x is irrational, then there are just two closed orbits on the boundary. There's a short one which goes around in one axis, and there's a long one which has action x, which goes around in the long axis. All the other orbits, it's basically the Hamiltonian flow. All the other orbits are non-closed. So the theorem is that if you have a genus 0, a rational curve, let's say a sphere with some holes in it, which has just one negative end, so it's actually a disk, with one negative end, which is asymptotic to a multiple of the short orbit. And if it's got, it got Fredholm index 0, so it's you look at, it's a J holomorphic curve, you look at the Cauchy-Riemann equation, it comes with index 0, then this curve persists under perturbation and stabilization. So it's a very robust curve. It's not going to disappear on you, whatever you do, which is very nice of it. So all you have to do is to try and find these degree curves. So if you find, why does it give you an obstruction? Well, if you've got a curve of degree d and end on this ellipsoid, then there's a measure, it's sort of symplectic area or symplectic action is d times mu, which is the size of the ball, minus n, because our ellipsoid was, its small axis was of size 1, so if you go around it n times, you have area n. So that's the size left over of the area of that curve. And the point is, if that curve is always there, it's symplectic, the area is always positive. So you get an embedding, you get the mu's always got to be bigger than n over d. So that's your embedding obstruction. So that's where these obstructions come from. And we want a curve which has got index 0, so it's rigid. And the index condition is 3d is equal to p plus q. So if you look at the obstruction, it's mu. So d is, it gives you mu equals 3x over 1 plus x, if you look at it correctly. So that's exactly the obstruction we want. And here, if you look at what curves we need, it has to be genus 0. Otherwise, when you stabilize, it'll disappear. And it's got to have a single end also, because if you stabilize, it'll disappear otherwise. So those are essential conditions. And so we have to figure out how to find these curves. And you can start with very geometric constructions, like having a curve in CP2 with suitable constraints in the ellipsoid and then just stretching it and see what happens. That's what we did when we did the ghost stairs, that sequence of even Fibonacci numbers coming down. But that's a very complicated argument, because all sorts of horrible things can happen when you stretch the neck. You don't want to do that. But recently I've been working on this problem and tackling it in many ways with Kyla Ziegel, and we're using many other methods, from tropical geometry, almost toric structure, scattering diagrams. I mean, a lot of methods from some of them scattering diagrams and tropical geometry sort of related to math physics ideas. And we're on the point of finding enough curves to prove this conjecture for CP2. So, we're using this problem as a nice geometric problem, that's a sort of target to try and understand more about what kind of curves you can see in 4 dimensions, the right kind of curves that extend, that will persist. And that's basically all I had to say. Here are some references.